Oh, yeah, one other thing I was going to show you. Let me pull this back up again. I'll stop the recording. So we were talking about triangles, and we said that there were the congruent triangles have everything the same. All the side lengths are the same. All of the angles are the same. Then you go to what we call similar triangles. So that's what we were talking about. So here's some pictures of the similar triangles. And basically they have the same shape, but they're either larger or smaller relative to each other. In this case, they've got them oriented is that a word? In the same direction. They don't have to be oriented. It's just easier to see that they're similar triangles. But the thing about similar triangles is all three angles are the same, but the lengths aren't necessarily the same. So one thing, these two triangles are similar. What I did, I think, is I made the smaller triangle and then just stretched it. But you can see how it fits in this corner, it fits in that corner. It's because all the angles are the same. So you can always stack them next to each other, at least in one of three corners. Now, the thing about similar triangles is that the ratio, the lengths of corresponding sides are the same. So what I'm going to do is I'm going to label these two triangles. The smaller one, I'm going to say this side has length A, this side has length B, and this side has length C. And in the larger triangle, I'll just use the capitalized version of the letter. And what we can say is that we can talk about the ratio of the sides. So these are just pure ratios, meaning one number divided by another number. And you can either go between corresponding sides, take the ratio between corresponding sides of the different triangles, or you can take the ratio of adjacent sides within a given triangle and compare them with the same adjacent sides in the other triangle. So let's show you both ways. So the first case is if I take the length of side A, the corresponding side in the larger triangle is capital A. And then if I take side B, which is a smaller value, and B is the bigger value, and we can do the same thing with side C. So here I'm comparing the lengths between similar triangles. Or I could say that this length, side A, to this length, side B, is the same as, within the same triangle, the same corresponding lengths. And you could do that with all sides. You could comparing all three sides. So here's A and B. I could do A and C, and I could do B and C. And these give you the same information. So let's just make up an example that kind of fits my drawing. So let's say that if side A has length 10 and the corresponding side on the larger triangle has a size 15, and the size of side B here is maybe 4, what is the length of side B? Question mark. So that's the side that corresponds to this side. So you can use either one. So let's use both of them and show you get the same answer. So using the first relationship, I would use this, just the first equality. So I'm going to use this one, A over A equals B over B. So small a is 10, big A is 15, small b is 4, and x is unknown. So to solve for x, you cross multiply. That means you take this times that, and you set that equal to that times that. So you get 10x is equal to 60, or x is 6. Well, I used x. I should have used capital B. Let me fix that. Sorry. You can leave it as x if you want to. Let's make this B. So the length of side B is 6. And you can see 10 divided by 15 is 2/3, and 4 divided by 6 is 2/3. It's the same ratio. So that's using this way. The other way of using would be this one, for the second way of looking at the ratios. So we're going to use A over B is equal to capital A over capital B. So small a is 10 units, small b is 4 units, capital A is 15 units, and I don't know side B again. So again, I cross multiply, and I'll get 10b is equal to 15 times 4, and you can see it's the same thing that we got before, same equation. So you still get b is equal to 6. So either way works. You can compare the same sides on different triangles, or you can compare adjacent sides on the same triangle versus the same two sides on the bigger triangle. And you don't need to, you don't need to know the angles, you don't need to know anything, you just need to know that the two triangles are similar to each other. So when for example, using this particular software, I can make a triangle like that, and one of the features of this thing is if I clone this, I will create something that's exactly the same, which is going to be congruent triangles. But if I stretch it, this new triangle that I've created is just the same triangle, but it's just scaled up. Scaling is something that's used all the time in mapping, in drawing buildings, in a lot of things, even just taking photographs of something, an animal, and you might want to compare, the relative size of things on one animal with the relative size of things on another. You might be scaling, or if you want to make models of airplanes, you want to test them, and all that it involves is looking at simple ratios. This is an example. You don't need to write this down. This was just to show you that you use this in even higher level mathematics. This was a calculus problem. And the question was, this guy's walking away from this lamp. So there's a lamp on a post, and the lamp is creating a shadow. So this is the person's shadow. And the question is, if this guy's moving at say 3 miles per hour, how much is the length of his shadow increasing? How quickly is the length of his shadow increasing? So as he walks away, this angle between the lamp and him becomes small. His shadow gets longer, basically. So so his shadow length is growing, and calculus tells you how fast it's growing depending upon how fast he's walking and where he is relative to the light. But to generate the equations necessary, you create a triangle here, which is the triangle associated with the guy, the ground, which is his shadow, and the distance from his head to the ground. And the other triangle is from the light to the ground to where the head of this person is, back up again. And because these two triangles have the same angles, they're both 90-degree triangles, they have the same angle here, therefore these angles are the same. They're similar triangles, and you can ratio lengths, and you can solve the problem that way. So before we get to actually doing calculations where we're going to ratio lengths, we have to recognize which sides correspond. If you have two similar triangles, which are the sides that we have to compare to be accurate. So you've got a couple of problems where you are going to identify the corresponding angles and the corresponding sides, and not just pointing at them and say, these are the two. We have to specify the angle and the sides using some terminology, which we've learned. So this is problem number 15 in your book. I think you have one or two problems. So let's do the angles first. And I'm just going to write this corresponds to that. So what we have is we have this triangle, and we have this larger triangle. And the reason they're similar is because this is a right angle, and this is a right angle. So there's one angle that's the same. And these two angles are the same because they're vertical angles. So because these two are the same and these two are the same, the third angle has to be the same as well. So all three angles are equal. And so you can see this angle, it represents the angle between the one that's parallel to the horizontal and the diagonal line. So this angle corresponds to that angle. So the way we would do it is we would use these letters. So I would say angle, and let's do this one first. Well, actually, let's do this one first, the single sweep. So this angle is HGK. And that corresponds to this angle. So this angle corresponds to this angle. And I'm going to start with the letter that represents this 90 degrees. So I'm going to start at the corresponding point, H, in the other triangle, which is F. So that corresponds to angle FGE. So that's this angle, FGE, HGK. And there's two other angles, so let's go to the next angle. So that's angle GHK. Corresponds to angle GFE. And finally, the one with the three sweeps is going to be angle HKG. And I'm just going to use my little ditto marks here, so I'll have to do this again. Corresponds to angle, so HKG, FEG. So you might want to go back later and just make sure you're understanding what it is. So those are the three corresponding angles. So as a consequence, these are in similar triangles, corresponding angles are the same value. So these two angles have the same value. These two angles have the same value. Now, as far as the sides are concerned, that's the more difficult one. So we've got three sides, 1, 2, 3. So I'm going to take this side, and so I'm going to say side, and I'm going to show it as a line segment. So it's line segment GH. The side that corresponds to this side on the other triangle is this other vertical line. I'm going to start at the same point, which is right here. So line GH corresponds to GF in the other triangle. Then we have this diagonal line. So here we have GK. So GK corresponds with GE. And then finally, which one haven't we done yet? The horizontal line. So the horizontal line is HK, and that corresponds to FE. Now, I'm not going to ask you to do this on a test. You're going to have to be able to look at them and say, these sides correspond to each other, and you'll use that information. This is just to beat it into your head that you know what you're doing. Okay, you don't need to write this. Let's just talk about this. It was one of these green boxes in your book. So there's one thing about an isosceles triangle, which is what we have over here. And it just helps analyze isosceles triangles in real situations. If you take a line from the angle that is between the two equal sides, so this side length equals this side length, and you take a line and you bisect this angle. Bisect means you cut it in half. That line will go all the way down to the other side and intersect. And it'll intersect it at a 90-degree angle. So this angle between here and here is 90 degrees. And the angle between here and here is 90 degrees. And so what we do is we convert this isosceles triangle into two similar, or actually congruent, right triangles. And what the advantage of breaking it up into a right triangle is you can use all the trig functions that are associated with right triangles. In this case, they're not talking about trig functions. They're just saying if you take this it says if this is an isosceles triangle, meaning that these two sides have the same length, and if D is the midpoint, meaning halfway between A and C, and you draw a line from this midpoint to the opposite angle, the properties that result are that these two angles are equal to each other. The angles created by this bisector, so angle ABD and angle CBD, are the same, and these are both right angles. So because of that, you get two right triangles, which are easy to solve. So it's just kind of an interesting thing, but we're probably not going to use that in this class. There is one similarity property for, this is kind of like the angle side and side angle side, whichever one we said. I forget which ones were the ones we used. Let's go back here. We had these rules that applied to congruent triangles: side angle, side angle, side angle. Okay. There is an equivalent type rule for similar triangles. There's just one rule. The rule says if the measures of two angles of one triangle are equal to those of two corresponding angles of a second triangle, then the two triangles are similar. So let me just draw a triangle and explain what this is saying. So here's my arbitrary triangle. And now we'll group them together so it actually is a triangle. And I'm going to clone this thing, and I'm going to shrink it. There it is. So now these are two similar triangles. So what it says, let's say this angle is 50 degrees, and this one's 50 degrees. And this one is 45 degrees, and this one is 45 degrees. So we have two similar triangles. Actually, we have two triangles where two of the corresponding angles, this angle and this angle, this angle, that angle, are equal to each other. As a consequence, the two triangles are similar. So the way you prove this is we know that the sum of the angles inside a triangle equal 180 degrees. So because this is 50 and this is 45, you add them together, you get 95. Subtract it from 180, you'll get 85. So this angle would be 85 degrees. And you can do the same thing here. This is 85 degrees. Well, now you have all three angles equal to each other. As a consequence, because all three angles are equal to each other, then the triangle is they're similar triangles. So it's just kind of saying, well, you only need to know that two angles are equal to each other. As a consequence, the third angle is equal to each other. As a consequence, it's similar. It just leaves out one step in proving that triangles are similar by just specifying two things. Just like we only have to specify a side, an angle, and a side. Two sides and one angle is enough to say that all the other stuff is equal to each other. In this case, knowing that two angles are equal to each other is enough to say that the third angle is equal to each other. And all the sides have proportional lengths. So these problems fairly kind of pretty simple. What they're asking you to do is to look at these two triangles. Notice that this angle is equal to that angle. And this angle is equal to that angle. So by just recognizing that these are similar triangles, we can say once they're similar triangles, then we can figure out the unknown angles. And I guess the question is, I think they're actually referring to these angles. This, because they haven't put the numbers there. I'm going to cheat in my book here. Now that I did it, I'm like, does it even care about what that third angle is or not? So let me see what the answer is to this problem. Sometimes you don't know exactly what they're looking for. Okay, so they're actually asking for all angles. So the remaining angle, we just use the same thing we did here. We take 180, subtract the sum of the other two angles. So we got 180 minus 134, which is 44. Oh, 42. I don't. Yeah, thank you. Yeah, correct that. 42 and 90, which is 132. So that's 48, I guess. So this one's 48 degrees. This one's 48 degrees. So you just need to draw the triangles, fill in the numbers. So same thing here. So this angle is 30 degrees. This angle is 30 degrees. This angle is 106 degrees. And then the final unknown angle you can calculate by taking 180, subtracting the sum of the other two angles. So you get 180 minus 136, which is 44. So this angle is 44 degrees. So that's all. We're just dealing with the angles of similar triangles. Now we're going to deal with lengths here in a second. So then you've got a couple where you've got similar triangles, and they're similar because this angle is equal to that angle, and this angle is equal to that angle. As a consequence, they're similar triangles. This angle will also be equal to this angle, but we don't need to know that to make the conclusion. Now what we have is sides. So there's two ways of solving this problem to get the same answer. We can compare corresponding sides, or we can compare adjacent sides. So this is corresponding. I'll say it's corresponding sides. So what I mean by that is I'm going to compare this length to that length as a ratio. This length to that length is that length to that length. And I cross multiply, divide by 6, and I'll get x 6. So that's the answer, x equals 6. Now if I do adjacent sides, so what we have there is I'm going to compare this with that and this with that. So I'll have 6 divided by 4 is equal to 9 divided by x. If I cross multiply, I'll get the same thing. 6x equals 36, and x is equal to 6. So either way, you get the same answer. So those are real easy. I mean, those kinds of calculations. I usually put one on the test that's like the next problem, and people always get it wrong. So here we have two triangles. We have a right triangle like this, and we have a right triangle like that. I'm going to tell you what people do that's wrong, and then I'm going to show you. Don't write this down. I'm showing you it's wrong so you don't do it wrong. You do it the right way. What they'll do is something like 50 divided by 100, which is these two sides, is x divided by 120. Because they'll just think, oh, you have similar triangles, there's 4 numbers, I'll take some ratios, I'll be able to get the answer. They don't think hard enough. So what we're doing here is you're comparing. In this case, I'm comparing them within adjacent sides. So I'm comparing this side to that side, and this side to, I didn't get the whole side. So you've got to make sure you include the entire side length, not just the number that you first see. So what the correct ratio would be, well, before we even do that, let's just, let me just point out the triangles here. This is the small triangle. We've got this common angle. We've got both right angles. The second triangle is this whole thing. So we got to include the whole side. So this is wrong. What you should do is either do 50 divided by 100, which is this side to that side, is x, which is the corresponding side on the larger triangle, and you add the two numbers that make up the longer side of the larger triangle. Or you could do it between corresponding sides. So I could do x over 50, so this to that would be this whole thing, 100 plus 120 to this side, 100. And you can see if I cross multiply, I'm going to get the same result. So remember, if you have a situation like that, make sure you include the entire length of the larger triangle, not just the part that you see. It's kind of like you guys who messed up the Venn diagram and just started putting numbers everywhere because it seemed like you didn't think that extra little step. Okay, then they give you some word problems, so we're going to go through those, and those are the ones that you're more likely to see on a test is these word problems. And the common thing you'll find out is that they're talking about photographs versus real things. So photographs are just smaller representations of the big thing that you see, or maps. Maps are smaller representations of the bigger picture. So we're scaling things. So what it says is that a photograph of a triangular piece of land, it says the length of the three sides are 4, 5, and 7. So let's make up a photograph here. 4, 5, make that a little longer, 7. Okay, so there's my picture. This one's 4 centimeters. This one's 5 centimeters. This is 7 centimeters. And because it's a photograph, all of the lengths should be scaled appropriately. So I was going to grab this thing, just make it bigger. It won't, it's not going to be scaled to the appropriate size because otherwise you wouldn't be able to see either the small or the big thing. But I'm just going to say it's bigger just to show that it is scaled. So here's my bigger picture. This is the actual land. So the shortest side of the actual piece of land is 400 meters. So what you do is you say, well, this is the shortest side of the photograph. So this corresponding shortest side of the land is going to be that. And because all these angles are the same, this angle is the same as that, this angle is the same as that, same as that, they're similar triangles. So all I have to do is take ratios of lengths. So it says find the lengths of the other two sides. Let's call this side A and this side B. And we know the ratio, you take the ratio of the known side. So what we'll say is 4 centimeters is to 400 meters as 5 centimeters is to whatever the corresponding side is, which is A. So we end up with a ratio. We can cross multiply. I'm leaving the units on here for right now, but as long as you are consistent, you don't have to worry about it. So I've got A times 4 centimeters and 5 centimeters times 400 meters. And then I divide both sides by 4 centimeters. So the centimeter units cancel out. And that leaves me with meters, which is what I would have expected. And if you do the calculation, you'll get 500 meters. Because 400 divided by 4 is 100. 100 times 5 is 500. So this one's going to be 500 meters. And you can almost figure B is going to be 700 meters. It's just a scaling factor of multiplying this by 100. So that's the other thing about similar triangles. You kind of have like a scale factor, which you can apply to. And actually the scaling factor, so what is the scale on this map? It would be 1 centimeter equals 100 meters. Because 4 centimeters equals 400 meters, so 1 centimeter equals 100 meters. Yeah, the last one was a scaling of 1.5. So if you had a photograph, you'd say, you could have a little scale on it, and then you'd be able to measure centimeters and then multiply it by 100, change the units to meters, and then you get the actual answers. That actually reminds me of something. Yeah, I'm trying to think of how to explain this. So, without showing the video, because I probably can't find it quick enough. So here's the story. So they did these initial nuclear tests, and they didn't tell anybody what the magnitude of the nuclear, 100 megatons or whatever the scaling factor is. And that was supposed to be a highly guarded secret. But somebody in the Army or whatever in the government decided that they still wanted to show people pictures of what they look like. So they published some pictures in Life magazine, some very well-known magazine. And this guy who's a physicist took the pictures and did some estimates. He measured the sizes, he took the photograph and he measured how fast the cloud was being created, because they actually left on timestamps on the pictures. And by looking at the times and how quickly the thing grew and using some kind of basically scaling things, he was able to come up with an approximation of what the energy of the nuclear explosion was, which was supposedly a highly guarded secret. And so he published that somewhere. I don't know if he did it as an actual article or he just told people. And then the next thing you know, the government's coming to check him out. Like, do you have some kind of inside, you probably got some spy on the inside. Yeah, and he says, no, I just measured it with the ruler and did some calculations, and they came up with, that was the answer. Yeah, I'm not sure. I'm not sure if he's American or one of the Nazis that came over afterwards. Yeah. Okay. So that's what you do with similar triangles. You're going to just ratio sides. And the last topic in this section is the Pythagorean theorem, which again is something that you've seen before, but I'm attesting to the fact that it's used a lot. Okay, there are things that are used all the time, and the Pythagorean theorem is used all the time. It's extremely useful in engineering and science. And what the Pythagorean theorem says is that if you have a right triangle, that the square of one length, the length of one leg, plus the square of the length of the other side is equal to the square of the hypotenuse. So if you have a right triangle and you know two sides, the length of two sides, you can calculate the third side. I think I showed you all those proofs. I did. I know I did. There are 200 proofs of the Pythagorean theorem. And I said at the time, you can see how important it is because they tried to come up with all these proofs. So what kind of things might you have associated with the Pythagorean theorem? Well, let's make up a right triangle, and we'll just do the calculations. I usually include something like this on the test too. So what you might be given is that side A is equal to, say, 19, and side B is equal to 10. The question is, what is the length of side C? How do you do that? Well, what we have is A squared plus B squared is equal to C squared. So we plug in the values for A and B. So make sure you can do this on your calculator. So then you, hopefully I brought my calculator. There it is. Yep. So you take 19 squared, which is 361. 10 squared is 100. So C squared is equal to 461. Therefore, C is equal to the square root of 461. And if you actually plug in your calculator, 461 square root is 21.47. It's an irrational number. It's a square root. It's not a perfect square. So the unknown side is 21.47. It's always longer than the other two sides, of course, because this is diagonal. And the closer, the smaller one of these angles is, the closer one of the sides is equal to that. So, this is 19. This is only 21.4. It's only 2.5 units longer. If you're ever walking, well, if you're ever walking and you decide to take a shortcut, you can see why taking the shortcut across the field is much easier. If you go around the field, you're going to add these two lengths together. 10 plus 19 is 29, whereas if you take the diagonal, you only have to walk 21 units, whatever those units are. Yeah, let me see if I can find a picture here. That reminds me of something. I'll share this with you. So this is the drill field at Tech, and nowadays they paved it. It used to be this is the side where that's the gym, and the dorms are over there, and then all the classrooms are on this side. Most of the classrooms are on this side. So they used to have these paved paths, one going straight across here, one going across there, and one going across there. But because nobody was going to walk this way and that way, they found the naturally shortest paths, which is a straight line right across the drill field. So this also used to be gravel, but they finally paved it. This one they haven't paved yet. This one. So this is the natural path that people take to go from one part. Apparently nobody goes from here all the way down to there, even though there is this diagonal that goes to that point, which is kind of interesting. I guess people, I'm not sure what the reason why there's not one that goes like over here. And there's not ones that go here. Hmm? Oh, no, I don't think so. I mean, this is just people wearing down the grass. So here's the reason these are going this direction. So if you're walking from the normal dorms, you come down this pathway, and then the big classrooms, like used to be for math and other stuff, is in McBride Hall. So you would go right through here. The engineering buildings are back here. So you would come down from your dorms, and then you would cross there to get. This must be the. That's where the memorial is for the shooting. This is the English building, and part of the reason I think is that not many, the dorms, they're slusher, but for whatever reason, nobody ever went here or there. I don't know. I never noticed that, but it's kind of interesting. Anyway, so you can see we have right triangles too. That's another. And of course, people say this is the coldest place on Earth during the winter because you're walking across there and the wind is blowing. That must be the Corps of Cadets right there, standing attention. So the other case would be, let's say we're given the hypotenuse. So we're going to make up another triangle. Let's make it this slightly different. So here's our triangle, and this is again a right triangle. So let's say this is equal to 15, this is equal to 10. What's that equal to? Again, because it's a right triangle, we can use the Pythagorean theorem, so let's call this side A. So what we'd have is a squared plus 10 squared is equal to 15 squared. And then we'd square them out, so 10 squared is 100, 15 squared is 225. Then you subtract 100 from both sides. So you get a squared is equal to 125. And a is equal to the square root of 125, which is 11.18. So apparently I didn't draw that to scale because that's actually smaller than 10, but since I just made those numbers up, this is probably greater than 10. So that's all you have to use the Pythagorean for, is just be able to find the third side. If I give you two sides, what's the other side? And only Pythagorean theorem only works for right triangles. Oops. Okay, so I already did one, so we're going to skip over that. The book tells you, well, this is a good example. If you solve for the unknown side here, it's 24. And when you have whole numbers or integers, I guess both of them, positive integers, whole numbers, if they are integers, then they're called Pythagorean triples. And if you take a math course, a lot of times they'll give you Pythagorean triples so you don't have to deal with square roots or anything like that. Or you don't have to deal with irrational numbers. So this squared plus that squared equals that squared. So the question is, how do you come up, if you were a math teacher and you wanted to come up with an example that had integers, how would you come up with those examples? So they just show that there are various formula that people have come up with that generate Pythagorean triples. So let's just use this formula to show you how it works. So let's, what you do is you pick both an R and an S value, and then you calculate from that an A, B, and C. So the case I wanted to show here was, let's pick R equal to 3 and S equal to 1. So the first formula would be 3 squared, R squared, minus S squared, which is 1 squared. So that's 9 minus 1, which is 8. B would be equal to 2 times R times S, which is 6. And C, which is the hypotenuse, would be 3 squared plus 1 squared, which is 10. So that is an example of a Pythagorean triple. So if we drew a triangle sort of like this, it says the shortest side would be 6, the next side would be 8, and the hypotenuse would be 10. But if we divided them all by 2, you would get 5, 4, and 3. So this this particular choice of R and S generates a triangle which is equivalent to the 5-3-4-5 triangle or 5-4-3 triangle. You know, that's the one that everybody uses to demonstrate. And there's these other formulas. I'm not even going to bother fooling with them, but they're just other formulas that generate other Pythagorean triples. So they're just special combinations of numbers that work out where an integer squared plus another integer squared equals a third integer squared. So now we got some word problems that involve Pythagorean theorem. So how do we know that we use the Pythagorean theorem? Well, because it says right triangle. So if you see anything that says right triangle, use the Pythagorean theorem. If it just says two triangles that are scaled, then you would use the ratio of sides. You'd use the proportionality. So it says the hypotenuse of a right triangle is 1 centimeter more than twice the shorter leg, and the longer leg is 9 centimeters less than 3 times the shorter leg. Find the lengths of the 3 sides of the triangle. This is just a way of using the Pythagorean theorem to create an equation that you solve for an unknown. I wouldn't put something like this on the test because it takes a little thinking. I'm just going to demonstrate how this works. So we're going to have a right triangle that has a shorter leg, a longer leg, and a hypotenuse. So let's draw it so we can think about what they're asking. So there's my right angle. It says the hypotenuse of the right triangle, which is this, is 1 centimeter more than twice the shorter leg. So if I let the shorter leg be x, then the hypotenuse is twice the shorter leg plus 1. It's 1 more than twice the shorter leg. So what I've decided to do is I've decided to have the shorter leg be represented by the variable x. Then I go to the next part of the problem. The longer leg, which is this side, is 9 centimeters less than 3 times the shorter leg. Well, the shorter leg is x, so the equation that represents that side is 3x minus 9. The longer leg is 9 centimeters less than 3 times the shorter leg. So now it's like all those other problems. I've created an equation where I've fully specified the problem. Now I'm going to use the Pythagorean theorem to solve for x. So what does that mean? It means that 3x minus 9 squared, which is the length of the longer leg, squared, plus the length of the shorter leg squared is equal to the hypotenuse squared. So this is not, you actually have to factor. What we're going to do is we're going to multiply everything out, combine all the like terms. We're going to end up with a quadratic equation, which we then have to solve however we want. We could either factor it or we use the quadratic formula. I think we can factor it based on what I remember. So when you have a quantity squared like this, it's like taking the quantity and multiplying it by itself. If I square x, I just get x squared. And then the right-hand side, when you square that, you take the quantity and you multiply it by itself one time. It's just, instead of multiplying, 3 squared is 3 times 3. So here I'm squaring this thing, so I have to take this thing and multiply it by that thing. Then I use FOIL to multiply both of those terms out. So 3x times 3x is 9x squared. So that's the first. Inner is negative 9 times 3x, which is negative 27x. The outer is negative 27x. And the last is positive 81. Negative 9 times negative 9. Then I add my x squared. And then I do the same thing for the second to the right-hand side. So 2x times 2x is 4x squared. 2 times 2 is 4. X times x is x squared. Inner is 1 times 2x, which is 2x. Outer is 1 times 2x, which is 2x. And then last is 1 times 1, which is 1. So now I'm going to subtract all this. Well, I'm going to combine these first. So I combine these two terms, which are both x terms. So that's the right-hand simplified. And then I'm going to subtract this from that. I'm also going to, before I do that, though, I'm going to combine like terms. So let me do that. So we've got 9x squared plus 1x squared, which gives me 10x squared. 27 and 27 is 54, so it's negative 54x. And then you add 81. So that's the right-hand side simplified. And then what we'll do is we'll subtract 4x squared, we'll subtract 4x, and we'll subtract 1 from both sides to get 0 on the right-hand side. So 10x squared minus 4x squared is 6x squared. 54x minus 4x is negative 58x. And 81 minus 1 is 80. That equals 0. So to be able to solve a quadratic equation, you combine like terms, you solve for all the stuff on one side, set equal to 0, and you say what values of x will make that be 0. Typically there are two values of x. There are either two values of x or no values of x. There may be no values that make this work, but in this case there are. It'll turn out that one of the values of x is positive and one of the values of x is negative. And so we only use the positive number because you can't have negative lengths. Okay, so now can we factor this thing, or not? How do we solve this thing? So let's think about this. First I got to make sure I did it right here. So before we go too far, we don't want to have a mistake. So that looks right. I'm just writing it down again. Can we simplify this by dividing by through a common factor? Well, yeah, we can divide by 2. So we'll get 3x squared. And if you divide that by 2, you'll get 29x, and you get 40. So usually when I have this not being 1, I usually use the quadratic equation. But I think you can actually factor this. So let's try factoring it anyway. See what happens. A little review here, factoring. So if you can find integers, this has to be 3x and this has to be 1x. 1x times 3x is 3x squared. And then these can be any factor, any of the two factors of 40. 1 and 40, 2 and 20. What would be next? 5 and 8. 4 and 10 is 1. So you got to kind of figure out which ones might add up to 29. Actually, they're both going to be positive. I just thought about, well, actually, yeah, this is positive, so, and this is negative, so, that's a problem, I think. Oh, no, it's not. Okay, so if you have two negative numbers here, they should multiply together will give you positive, and then added together will give you negative. So let's just try a few things here. So what do we have? We have 5 and 8 and 4 and 10. So if I put 10 here, I'd get 10 times 3, which is 30, which is more than I need already. So that's not going to work out. Or unless I did it the other way. 10 plus 12 is 22, so that one doesn't work. And let's try the 8 and 5. I think that actually doesn't work. So this is going to be 8 and it's going to be minus because I have a negative. So I knew these two multiplied together had to give me 40. They had to be both negative because I got a positive number and I have a negative number here. I said 10 and 4 didn't work, so I tried 5 and 8. And I put 8 here, and I've got 24 plus 5, which is 29. So that actually does work. So that means my two solutions are going to be 3x minus 5 equals 0. So for this product to be 0, either this has to be 0 or this has to be 0. So those are my two solutions. So one solution is x equals 8, or x minus 8 equals 0. And the other one is x equals 5/3. So I get two answers. Now only one of the answers is going to work. So what you do is you go back and look at your original problem. And what you'll see is if you use 5/3 or whatever the answer was, 5/3 here, this number will be less than that number when you multiply it out. So you can't use the smaller number because you'll end up with a negative side length. So that means my only other choice is 8. So to make this whole thing work out, x has to equal 8. So we're going to write that down. So this is 8. This is going to be equal to 17. And this is going to be equal to 24 minus 9, which is 15. So let's just double check. Let's take 8 squared plus 15 squared is equal to 289. Take the square root and you get 17. So this is a Pythagorean triple. And you see it works out. So let's go back and check it. The right triangle, let's see, the hypotenuse is one more than twice the shorter length. So the twice the shorter length is 16 plus 1 is 17. And the longer leg is 9 centimeters less than, well, we know they're right because I use those to calculate it. So anyway, that's how it works. Like I said, you're not going to be able to figure that out, but it's a little review, a little algebra review. We use the Pythagorean theorem to generate the equation that we solved. Okay, the rest of them are easier than that. So this actually is a scaling thing here. Imagine a carpenter building a floor of a rectangular room. What must the diagonal of the room, oh, okay, this is actually a Pythagorean theorem thing. What must the diagonal of the room measure be if your floor is to be squared off properly?
So I hired a carpenter to get me to take measurements for me.
Well, interestingly, this is actually what carpenters use, this exact procedure. When they're building a house to make sure that the walls are squared with each other, what they'll do is you'll have one wall that's straight. And you'll know it's straight because you'll take a piece of string and you'll attach it between two posts and you make the string taut. And then you dig a trench and you lay your block and so that they all align with the string. So you know one side of the house is straight. Then you come to the corner and you take whether it's a tape measure or just probably pieces of string that are the right length. And what you'll do is you'll have some, let me just see if I can show you how it works. So what you'll do is you will, so here's the side that you've built already, which you know is straight. So there's your block. And we're looking down on the wall, down on the block. You come over here and let's say you have a piece of string that is 10 feet long. So you'll go actually 8 feet long. So you go this way along the straight wall that you know straight. This is 8 feet. Okay, so you can, then what you'll do is you'll take another piece of string and you'll walk this way, but you don't know exactly which way to walk. So you'll walk approximately perpendicular. So we'll make this 6 units. So I'm going to make it slightly off So we'll correct it here. Then you have another person. You probably don't need all these people, but what you'll have is a piece of string that's 10 units long. So this is 10. And what you'll do is you'll have this person walk over like this, and they'll be creating a circle basically in that direction. And so then this person will take it and rotate around, and this person will, and then you'll get to the point where you both meet. So the person here holding the string meets the person holding the other string, and they'll have the strings taut, and then they'll put a stake in the ground right here where the point is that these two guys run into each other. And then you take this stake, and then you take a piece of string and you pull it tight, and then you build your wall this way. And because of these lengths, because it's a 3, 4, 5 triangle, this stake that you put into the ground will be exactly perpendicular. This line created by that will be exactly perpendicular, and that's what they do. Okay, it's not made up. They actually do that. So in this case, what they're saying is, what must the diagonal be? So they're saying this one's 14, this one's 20, this is x. So all you have to do is say x squared is equal to 14 squared plus 20 squared. So 14 squared is 196 plus 20 squared, which is 400. So you'll get 596. And then you take the square root, so x is equal to the square root of 596, which is 24.413 feet. And it says here round to the nearest inch. So you have to convert this decimal into inches. This is decimal foot. So to get to the inches, you would take the decimal foot and you would multiply by 12, because there are 12 inches per foot. So 12 times 0.413 is 4.956 inches. So the answer would be 24 feet 5 inches. So you're rounding off to the nearest inch, which 4.956 is pretty darn close to 5 inches. Now you wouldn't normally do this because this was not a nice, these are all nice things that you can look easily on a tape measure and do it. So nobody would do this. They wouldn't use these random lengths. They'd use lengths that they know work. They could use 16 and 12 and 24, depending upon how far you wanted to put this stake in the ground. But it's all relating to the Pythagorean theorem. So we'll start this, but we'll finish it next time, so we'll see how far we get. So this is actually a proof of the Pythagorean theorem. It's problem 81 in your book. It's just a showing using similar triangles how you can prove that the Pythagorean theorem is true. So it says in the figure, what we have is we have actually 3 right triangles. We have the large right triangle. And if you take a line from this point and you go perpendicular to this side, so this line is perpendicular to this side, you see the right angle. You create a smaller right triangle and then an even smaller right triangle. But because they're all right triangles, and it turns out that this angle here is equal to that angle, and this angle is equal to that angle, not only are they all right triangles, but they are all similar right triangles. You just have to correctly identify which are the corresponding sides. That's the hard part. So let's see if we can figure this out. So what we're going to do is we're just going to use the fact that similar triangles have similar proportions on corresponding sides. So it says by proportion we have that length C, which is the hypotenuse of the biggest triangle, to B, which is the longer of the two legs, is equal to something divided by J. So J is this length. So because we're comparing B with J, here this is the longer leg of the triangle. This is the longer leg of this triangle. Therefore, C, which was the hypotenuse for the big triangle, we have to use the hypotenuse for this intermediate triangle, which is going to be B. Okay, so we're saying this length to this length is the same as this length is to that length. Then it says, by proportion, we also have that C, again, the hypotenuse to A, so that's the hypotenuse of the big triangle to the shorter leg of the big triangle, is equal to A. Well, C is the hypotenuse of the big triangle. A is the hypotenuse for this small triangle. So what I'm going to do is I'm going to compare, in this ratio, A is the shorter leg of the big triangle. So what I need is the shorter leg of the little triangle. So the shorter leg of the little triangle is K. So that's K. And then what they say is, from part A, find what B squared is. Well, if you cross multiply, you'll get this times that equals that times that. So B squared is equal to C times J. And if you do the same thing in the second ratio, this times that equals that times that. So you get A squared is equal to C times K. And it says, from the results of here and factoring, what do you get? Well, if you take this squared plus that squared, it should be equal to this squared plus that squared. So let's see, I might even finish it today. So what we're going to do is we're going to say B squared is equal to O times J, and then we add A squared, which is equal to C times K. This must be a C and not a, that must be C, not, I wrote it incorrectly. C times J. So that's C. If you factor out C, you'll get C times J plus K. So A squared plus B squared is equal to factoring out the C, but J plus K, this side plus that side, is C. So you get C times C. And therefore, A squared plus B squared equals C squared, which is the Pythagorean theorem. Okay. Don't worry if you didn't get all that, but the trick here is identifying the correct corresponding sides of similar triangles. And I've done it multiple times, so I see it more quickly. So we'll actually do that again next time, and we'll try to see if you absorb it when it happens. And I will officially assign the homework next time. So here's the homework, but I already said the class is over. So.